So our speaker today is Chalabi from the Niels Bohr Institute, who will tell us about, turn.
Yes.
Turn. Will tell us about surface defects and integrability.
All right. Thank you, Andy. Thank you for being here. So today I'd like to say some words about a paper I wrote together with Chalabi Christiansen and Chen-Young Su, who are both at the Niels Bohr Institute. I bothered writing out Chen-Young's name because he did a lot of the computations in this paper, and he's very good. He's Charlotte student, and he's applying for postdocs, and you should hire him. And so the subject of this, the broad topic of this paper is surface defects and integrability. So we set out to study surface defects in n=4 super Yang-Mills theory using integrability techniques. And so in this talk, I'll first introduce the defects that we studied. Then I'll say some words about integrability and large engaged theories. So I didn't want to assume everyone was super familiar with this. I'll spend a bit of time on this. So if I'm going too slow, please stop me and I'll speed up. Then we'll move on to some results before we wrap up, and I'll present some of the open questions that we have. Cool. So let's get started. So the surface defects that I want to study in this talk are so-called Hooker-Witten defects. They were introduced by Gokov and Witten in 2006. And I kind of want to convince you that these are the simplest surface defects that you can write down in gauge theory. So let's start with, I wanted to start, instead of going to n=4, I wanted to start with Maxwell theory. Right. And then I want to introduce a surface defect along the z direction, and then it's propagating in time. So really, when I write z, it's also a time direction, and I'm just going to take this to be Euclidean time for the rest of the talk. And then there are two obvious operators that you can write down. Right. So the first one being this one, basically a two-dimensional theta angle, where eta here is just some number. And then here's another one, which instead of writing down the field strength, I will write down the dual field strength. Where here the integral is taken over my defect sigma. And so, if I don't want to write this in terms of the dual field strength, I can equivalently write my field strength in terms of some background configuration and then some fluctuations. And if I take my background configuration just be equal to 2 pi alpha, what's the notation I'm going to use? Sigma. 2, where this is a delta function. It's a two-form delta function that if I integrate it over the transverse space, just gives me 1. So if I take this field strength around this and plug it back in, expand around this background, I essentially get this operator here for the fluctuation. So instead of thinking of dual field strengths, I can just work with ordinary field strength if I want. So locally, I can write down this field strength in terms of the exterior derivative of some gauge field, which looks like just something like this, where theta here is a coordinate in the transfer space. So here it's an angular coordinate theta, and then I'm going to use a radial coordinate, which I will call r, in the xy plane. Cool. So this alpha here turns out to be periodic. And just by electromagnetic duality, where I exchange field strength and equal field strength, this guy better also better be periodic. So in Maxwell theory, these operators are kind of boring. They're topological. They're essentially the topological defect associated with the U1 electric and U1 magnetic one-form symmetries of Maxwell theory. But if you introduce operators that are charged under U1, then these operators become dynamical. They're no longer topological. And they become more interesting to study because they can also tell you about phases of gauge theories, depending on whether they confine or don't confine. So in this talk, not only do I want to introduce fields that are charged under these symmetries, under a gauge field, I also want to make the gauge field non-abelian. And so for concreteness, I'll take the gauge group to be UN. And then, instead of just having one parameter, I can introduce n parameters, which I will again denote by just an alpha, but you should think of this really as a diagonal matrix where I have a bunch of numbers I have a bunch of numbers, which are all periodic. I have n of these in total, and then I can take, say, some of them to be equal, if I want, but I don't have to. And similarly, I can write down something like that for this eta that I have in here, and then I should generalize my my surface operators just by sticking in some traces. And so these parameters, together with this partition of n, so here these ni, 1 to n, you better add up to n, the rank of the gauge group, for this to make sense. So really, this will be a partition of n, which I need to specify, which then will tell me how my UN gauge group is broken by the defect. Okay. So these are the defects that I want to study, but these are dynamical, but things become difficult quite quickly. And so what I will use is I will just impose lots of symmetry. The symmetries that I want to impose are n equals 4 supersymmetry, and I will just study supersymmetric versions of this. Or rather, let's say I will just study these systems in n equals 4 super Yang-Mills theory. I remind you, this contains a gauge field, it contains a bunch of 5 fermions, and some real hadron scalar fields, all of them in the joint representation. And as you all know, this theory is beta function of the Yang-Mills coupling vanishes, so this is actually a conformal field theory. So I really have a lot of symmetry at hand. And so if I take these operators here, and I insert them in n equals 4 sub Yang-Mills theory, these defects actually turn out to be half BPS, in the sense that they preserve half of the supersymmetry, half of the supercharges of my n equals 4. And since they're obviously scale invariant, so alpha and eta are just numbers, I have a lot of tools at hand. So it actually turns out that these are not just half BPS and scale invariant, they actually are super conformal. And so I can use a lot of techniques. So first of all, I can use techniques from supersymmetry, from conformal bootstrap. I also have everything is perturbative, so I can also use perturbation theory. I could use ADS CFT if I wanted, and as we will do in this talk, we can use large N integrability techniques.
Do those defects provide some boundary condition?
Both defects. What do you mean? So I mean, one I've written in terms of a boundary condition for the gauge field. The other one I could write in terms of a boundary condition in terms of the dual gauge field. But here you can just think of it as a theta angle that I can turn on the defect. Okay. All right, so I said that these defects actually are half BPS. And it turns out that you can actually introduce them simultaneously. So I can turn on alpha and eta at the same time. And not only that, I also have the freedom to turn on a bunch of other parameters. So if I take two of my adjoint scalar fields and write them, package them up into a complex scalar, then it turns out that I can introduce a background for this, which is constrained by supersymmetry to take this form. So beta and gamma are again diagonal matrices, exactly of the same form as alpha here. So I can basically turn on all these 4 parameters, or 4 sets of parameters at no extra cost, meaning I don't break any more supersymmetry, and you can see the way. And the reason is that there is some kind of BPS equation that involves these parameters that enter here. So a priori, these could be functions of R. And this guy too. And then there is some kind of supersymmetry equation, or a norm equation. Okay, so it turns out to be exactly Norm's equation. Dx1. This equation is obviously solved if all these matrices are just diagonal matrices and constants. And so in total, so as we'll see that the Kuka-Witten defect is described by these 4 parameters, which I'll just write out again, plus this 2d theta angle. And maybe say this partition of n actually that enters. So that's that's part of the crucial data that you need to find. Okay, so as I mentioned, so this defect preserves supersymmetry, and it's actually conformally invariant. Also, the singularity here of the gauge field is scale invariant. Sorry, the scalar is scale invariant. Turns out the full thing is actually super conformally invariant. So it preserves following subgroup. Of the four-dimensional superconformal algebra of n equals 4 triangles. It's not going to be hugely important to us what this algebra is. I just want to emphasize that inside there's the conformal algebra of 4 dimensions, and here sits the conformal algebra that's preserved by the defect. So it's a 2-dimensional conformal algebra. And so I really have a defect conformal field theory, and I can use tools of DCFT. Yeah.
How come supersymmetry doesn't force some relation between A classical and phi classical? Is it just...
it comes out of a calculation, right? So yeah. So normally you would expect that, but for this defect it doesn't. I'm not sure how. If there's an easy way to see that, but it's worked out in a number of places. So I think in Gukov and Witten, they find these supersymmetry equations by reducing to 2 dimensions, and then they find some kind of like a 2-dimensional sigma model, and then these supersymmetry equations, they correspond to some equations that the Higgs field needs to satisfy. But then it's also been worked out explicitly just by looking at how to embed this algebra into parent algebra. I think in a paper by Matsura and Gomez a couple of years later, and this is what you find.
Is there some more general class of defects where there is a relation between the two, or?
I'm not sure. I don't know. For half PPS, I think you really need to satisfy this equation. So I don't see how that would.
Related to my question of, it seems like a trivial solution of that equation that people study non-trivial.
Very good. I'll get to that in a minute. Yes. Good. Then let me just, before I get to Andy's question, let me just say very briefly that so I will have local operators in the bulk, just to set the notation that I will label by some scaling dimensions, delta, capital delta, and j, some of the quantum numbers which I won't care about, for operators on the defect, labeled by lowercase Greek letters. And then, using the OPE and defect operator expansion, you can decompose all kinds of higher correlation functions into smaller ones, which are then just labeled by 3-point functions of those guys, 3-point functions of these guys on the defect, and then the bulk to defect 2-point functions. And in this talk, I will study μ's with, so bulk to defect 2-point functions, where I take the operator on the defect to just be the identity. So really I'm studying 1-point functions of bulk operators. So this is the DCFT data that I want to study in this talk. In particular, I want to study, well, okay. Yes. So I want to study 1-point functions of operators that are built out of scalars, which will take this form. And then since the defect actually breaks rotational invariance in the transverse directions, there can also be some phases here. But it's not hugely important. Okay, now to get to Andy's question. Andy just walked out. Okay. So to get to Andy's question,
That's A sub theta, not A times theta.
that's, sorry,
A sub
this
O.
is
I
A
see.
sub O.
Got it, thanks.
Sorry. And so, as Andy pointed out, this is kind of like a trivial solution of this supersymmetry equation. So I can also write, there's another obvious solution, which is just given by this, where these are SU2 k-dimensional SU2 representation matrices. And if you just, you take a derivative with respect to the logarithms, you find that you get something like 1 over log squared on both sides, and then this, whatever matrix you have here, that just has to satisfy the SU2 commutation relations. So that's just, that's also a good solution of the supersymmetry equations. And so these defects that were discussed by Gukov and Witten actually 2 years later after their first paper. They called them rigid surface operators because they don't depend on any continuous parameters. And so when we first stumbled upon them, we thought, okay, this is just some kind of weird, just some curiosity, right? Because they look kind of weird because you have some logarithms appearing, so it's unclear what's going on with scaling invariance. But it actually turns out that they will play an important role when we study integrability properties of surface defects. And so we were naturally forced to consider these kinds of defects.
I mean, it looks like something really weird happens if R equals 1, right?
Yeah, exactly. So you should think of this really as just describing the singularity of the defect. So I'm not sure you can really think of it as a classical field profile event which you can quantize. So in principle, the source of the equations of motion everywhere up to R equals 1, where the solution breaks down. So
I'm supposed to trust that it's small r? Or
so you're supposed to just, yeah, exactly, you're supposed to trust it at small r. Yeah, so this is the non-trivial solution.
One is what some Untitled for.
Sorry?
One is a scale.
It's unclear to us. I think Gukov and Witten, they really just care about the singularity itself, and they say that whatever scale you introduce, it's unphysical, and so really you should allow the scale to fluctuate, and correlation functions that you compute at the end of the day should be independent of the scale, or all physical quantities that you compute should be independent of the scale. But it's not quite clear to us how to do this, actually hands-on in perturbation theory, and so I don't really have a good answer to your question. Good.
It's an IR cutoff?
So the
Trusted at short scales?
you should trust it at short scales. You should trust the singularity at short scales, but then as you go further away, larger distances, something weird happens. Right? Solution breaks down. So really it's a statement that you should be, I guess in the path integral, you should be integrating over field configurations that have this kind of singularity. So if I write this out explicitly, right, you have something like a classical
you might also wonder, maybe it's really a short distance cutoff, and I should trust it at long distances when R is really big.
mean, the idea behind this is that really when you're writing down this solution in terms of these continuous parameters, so what you're supposed to do what you're supposed to do in the path integral is to sum over all field configurations that have this kind of that have the singularity as you approach the location of the defect. But then you're also allowed to include field configurations that have subleading terms. Right? So they will have a leading singularity that goes like 1 over r, and then they will have milder terms as they approach the defect. Right? And so what this is saying, in a way, is that if you dial alpha, beta, and gamma to 0, you're killing the leading singularity. But then you're still allowed to integrate over field configurations that have this kind of milder divergence as you approach the location of the defect. Yeah, it's a bit weird.
It's a puzzle, yeah.
Yeah. No, I'm not claiming we really understood what's going on. And I think it's fair to say that these kinds of defects, these ones, just write down the words, rigid, they're much less studied in literature. I think a lot of it is due to these weird logarithms. So I think there are very, very basic questions that I don't think have been understood in the literature about this system. Okay, so that's essentially what I wanted to say about the systems that we'll be studying. So let me say a few words about large N integrability, since I've mentioned it a couple of times already. And so, yeah, I will say a lot of basic things that you've probably heard before, so if I'm really going too slow, tell me and I will speed up. But since I didn't want to assume that everyone is familiar with integrability and large N gauge theories, I thought maybe it would be useful to some of you. Okay, so integrability at large N in gauge theories like N equals 4 or A by J theory is really a statement about the spectrum of these theories. And so I told you in this talk we wanted to compute one-point functions. So how do we relate this to? So how does that really help? So what I kind of want to do in this talk, I want to compute one-point functions in the most stupid way, right? So you could imagine writing down some single trace operator like this, built out of my adjoint scalar fields. I'll just call it O, with some indices. And so if I just want to compute one-point functions at leading order, what I can do is I can take each of these fields, phi, and just replace it by whatever classical field configuration whatever classical background this field should have. And so that just computes a one-point function to leading order. Right? But these operators O, those one-point functions I'm computing, they should be eigenstates of the dilatation operator. They should have a well-defined scaling dimension delta. And if I compute, so at tree level, the conformal dimension will just be L, the number of operators that I've inserted. But then, generically, this could, but if I start computing loop corrections, not only will this acquire an anomalous dimension, but operators of these types will mix with other operators. Or they'll mix with each other. So for example, if I compute the two-point function of O, maybe I'll want these downstairs. So if I compute the 2-point function at one loop order, I will not just get a term that corresponds to the anomalous dimension followed by a bunch of delta functions, where I just have delta 1, so delta j, I1, j1, and so on and so forth. But I'll also get terms that permute these in a weird way. And so it's the outcome of a computation that Joe Minahan and Kostis Irembo did in 2002, that if I do this in the large n limit, that I will get a logarithmic divergence, or I'll get a log divergence and times some stuff. And this stuff, so let's make sure I get all the signs and factors right. This is acting on delta functions. JL. Good. So this capital lambda is just a UV cutoff. This lambda is the 't Hooft coupling. And then instead of this, and so instead of just having one, you actually find some funny matrix here, where you normally expect the anomalous dimensions to sit. And so I should tell you what these funny matrices, how these funny matrices act. So this P is really a permutation operator. It permutes these two J indices on the delta functions. And this K, you can think of it as a trace operation. Okay. Good. Good. And so, yeah, as I said, so where you normally expect the anomalous dimensions to sit, you have this funny matrix, which I will call gamma, capital gamma. And maybe I'll erase this bit here. This gamma, it's a linear map. On some tensor product space. And so really, since these operators that I have here are defined in terms of the trace, I also need to add some, so when I compute the 1-point function, I will also have permutations of this, cyclic permutations of j. So this Hilbert space will also be invariant under cyclic permutations. And since gamma is built out of terms that I cycle along, well, from 1 to L, along some chain, this gamma commutes with this operation, this cyclic shift. Moreover, gamma is Hermitian, so I can really think of gamma as some Hamiltonian on some spin chain, a closed spin chain. So the picture you should have in mind is that I will have some chain here where I label my sites 1, 2, 3, 4, 5 up to L. And then basically for each of these sites corresponds to an insertion of my adjoint scalar field. And depending on which index I have, it will have some kind of spin. So something like this. And so you can think of gamma as really a Hamiltonian on this one-dimensional quantum mechanical system. And it's not only any odd Hamiltonian. This Hamiltonian turns out to be integrable. Meaning that if I write H, just in this way, sorry, I should start the notation gamma in this way, I can define some charge just in terms of the commutator of this thing. And this charge actually commutes with the Hamiltonian. And I can construct, similarly, I can construct higher charges out of this Q3. I'll get something like Qn, random rates are equal to 3, which all commute with gamma. So then an infinite tower of conserved charges in this system.
By putting the UV cutoff, do you mean that we cannot take the coincidental limit?
So this UV cutoff, it essentially just comes about from a diagrammatic computation, right? So you just you just bring down the full scalar vertex, and then you have an integral to compute in position space. That integral diverges as the points x and y collide with the insertion of your vertex. So you have to regularize that integral. And so this is this UV cutoff that appears. Or if you like, you can think of it as having something like 1 over x plus y raised to some power plus something small. And then you just expand around this something small and you'll get a logarithm. And this is just the scale that accompanies and so on.
Okay. Normally that gamma is related to the anomalous dimension, right?
Sorry?
Normally this gamma I wrote is related to the anomalous dimension.
Exactly. Precisely. This is where I'm going with this. Let's erase. Precisely. So really what I'm saying is that eigenstates of this gamma, they will correspond to eigenstates of my dilatation operator. So those are operators that have a well-defined weight on the dilatations. And
where is the other one term that you do this expansion?
oh, I've ignored it. Right, so this is just the one loop computation. There's a tree level part. that I've just not written out. But it's just the usual thing, right? It will just be this term,
Okay.
just the denominator here with the usual index structure. Nothing special happening there.
These operators, are they mixed with some other operators, or these are the only operators? Like a trace, more trace, or?
Very good. So at this loop order, these operators of this type only mix with each other. If I compute higher loop corrections, then I'll need to worry about the Yukawa interaction that I have in my Yang assumption. And then I can have mixing between operators of this type.
So it's higher loop, not in the higher end. It's the higher loop order.
Higher loop order in the Tuft coupling. I'm always in the large n limit, so I only so I ignore all non-planar diagrams.
But are they still integrable, or can they still be solved with?
So there is a way. So strictly speaking, no, you really need to be in the larger limit. But I think there are some efforts to go beyond strict linearity. Also, everything I say so far is okay. Sorry, maybe I'll make the comment a bit later. Yeah. Okay. And so so as I was saying, so this gamma, it's really, you should think of this really as corresponding to the dilatation operator. And so to find eigenstates of the dilatation operator, you need to diagonalize this gamma, and then the eigenvalues will just be these anomalous dimensions.
Well, that's related to the spinning index, but maybe there's no spinning.
Sorry? Okay, maybe you can ask me later.
Just to be clear, you'll always be at leading order large n and
Yes.
leading order in small e.
So in this talk, yes, I will just be at leading order in the Tuft coupling, at weak coupling, and always at large n. Strict large n limit.
If you go away from those limits, is there something like what happens to locality in Hamiltonian? Discuss.
Very good. So if you go to higher orders in the Tuft coupling, then you will also get longer range interactions on the spin chain. This is what generically happens. Right. So you can still, so everything I'll say about integrability, it still goes through. Almost everything I say about integrability still goes through when you include higher order corrections. It's just things become a lot more complicated because then you no longer just have local interactions, but also long range interactions in the spin chain. And so the loop order in the Tuft coupling corresponds to the range of the interactions. So things get a bit more complicated the more interactions the more orders you compute. Good. Okay. So here I've just focused on scalar operators. More generally, you can have operators. I can write down operators any type. Where I can insert some scalar here or some fermion. Maybe I can take some derivatives of my scalars and my fermions. Or I could also introduce some field strength tensors, which I use to decompose into soft-dual and anti-soft-dual bits, you know. And so this actually gives rise to a supersymmetric spin chain, PSU2,2/4 spin chain. So this is looking from an algebra of the n equals 4. And what do I want to say? And then you can consider closed subsectors of this, right? So things like the SO6 sector, which is just computed by looking at operators of this type. So this is what people often call the SO6 sector. It's this backbone as well. The SU2 sector, something the SL2 sector, and there are many other sectors that you can consider, which are all closed, at least a leading order in the Untitled company. Then, at higher orders, different sectors, these sectors may no longer need to be, or some of these sectors do not need to be closed anymore, and then you can have mixing between different sectors. But for this talk, we'll just be I'll just consider one loop dilatation operators, so I won't have to worry about this stuff. Good. Okay, so let me give you just a very brief idea of how the spin-chain Hamiltonian is useful. And I'll just do that in a very simple example, which is the SU2 sector, where instead of just having 6 scalar fields, I just pick 2 of them. Something like this. And so instead of now having a 6-dimensional Hilbert space at each site, now you just have you only have 2 dimensions. You can really think of this Z, for example, as a spin down on each side, and this X as a spin up on each side. If I have an operator of this type, Z, Z, X, Z, something like this, something complicated, well, not too complicated, I guess, with 2 operator insertions of X, I can map this to a state on the spin chain. 1, 2, 3, 4, 5. So I have down spin, up spin, down, up, down, and away. So I'll have some configuration like this, corresponding to this operator here. Now, in the SU2 sector, so if you just repeat this computation, that's on the board, but just for operators built out of 2 scalars, what you find for the matrix of anomalous dimensions is just it's really just a Heisenberg Hamiltonian, where this P is again the permutation operator. And so the ground state of this Hamiltonian is the state where all the spins are aligned. So I'll just take this to be the all down state, which I identify with the operator Z raised to the M, so just insertions of Z. And then I can treat insertions of spin ups just as impurities on this chain. So, good. So this operator by itself, it's not going to be an eigenstate of this Hamiltonian, because eigenstates of this Hamiltonian need to have all the x's permuted, right? Because I have a permutation operator sitting in here. But I can essentially find eigenstates in an efficient way using a technique called the beta ansatz, or precisely coordinate beta ansatz. And I'll just sketch the idea very briefly.
When you identify the operators to the state of the spin chain, you need to gauge the cyclic symmetry.
To gauge the cyclic symmetry.
Yeah, because if I rotate the spin, it's the same operator.
Yeah.
It's cyclic.
Yes.
So, but in the spin chain, it's not the same state.
I mean, I have translational invariance. I can just translate along the spin chain. It's a spin chain.
But each state is not translational invariant.
But I've set it up in a way that essentially I have this invariance property on my chain, right, on my Hilbert space. Maybe I don't understand the question.
Well, I take a generic state, not spin up or down, but some generic state. If I translate by one side, it's not the same state.
Sure, but you identify these states.
Exactly.
Yes.
That's what I'm saying.
Yes, yeah, you,
This is
yeah,
not
yeah, you have to identify.
engaging.
Yes, precisely, correct. Good. And so the way you do this is you basically take combinations of this type of operators with permutations of x, and then for each x, inserted at some site j, you would introduce something that looks a bit like a momentum. Write this like this, so this is my site j. And so you can think of this kind of as some kind of plane wave ansatz that you make. And this, so when you have more than one excitation, you have to be careful what happens when two excitations cross each other. So you need to include an extra factor, which is just the two-particle scattering matrix. Yeah, so basically you can write this. You can basically write any eigenstate. You can make an ansatz for the eigenstates of the Hamiltonian, just in terms of states of this type. And to solve it, it's useful to introduce something called rapidity variables. Which are often denoted U. And then you can ask, okay, what kind of values of U, or equivalently, what values of P are allowed such that this state, with this particular ansatz, is an eigenstate of my Hamiltonian. And the answer turns out to be given by the beta equations, which I'll just write them out very quickly. Just to give you an idea, this capital M here just corresponds to the number of impurities or insertions of X that I have. Right, so I just need to, so this is just a bunch of polynomial equations that I need to solve. And once I have a solution, I will denote them just by this curly bracket U. And I remind you that this just corresponds to one particular operator, which has scaling dimension L plus some anomalous dimension, where this anomalous dimension is just the eigenvalue of corresponding to this eigenstate, which takes this form to M. That's just this anomalous dimension. That's the very rough idea behind integrability. Sorry?
M.
M is the number of insertions of X. So here, M is equal to 2 in this example, but I could also have more insertions of X. Okay. So I don't have so much time. I'll be very brief. Let me just, another sector that you could study is the SL2 sector, where you have operators that are just built out of some scalar and a bunch of derivatives. L. And you can basically, so I just wanted to say that, I just wanted to give you this example because now the states that you have on each site, they can be associated with any positive or non-negative integer. So you have an infinite dimensional, you can also have infinite dimensional Hilbert spaces or spin chains with infinite dimensional Hilbert spaces. And then essentially the same kind of story goes through. We can find eigenstates via the beta ansatz and identify them with particular operators. And perhaps one more reason why I mentioned this is that since I said that, for example, the SO6 sector, once you compute higher order corrections and the 't Hooft coupling, you have mixing between operators that also involve fermions. So this sector is not closed at beyond one loop. Turns out that the SO2 sector is actually close to all orders in mediative coupling. Good. In the last 30 minutes, I wanted to say how this helps us compute one-point functions. And so, to compute one-point functions, it's useful to introduce something called a boundary state. And it's really just a state in the, it's just a state on my spin chain. Well, this here is the dimension of the on-site Hilbert space. So in this example, this would be 6. In the SU2 sector on the other board, this is 2. Here it's infinite. Omega here, you should just think of the classical background that you have. And in the case of the SO2 sectors, it's appropriate derivatives of this background. And this one here you just identify with one of the fields that you have in your theory.
So what's the sum over here? L?
So the sum is, the sum is over I, of course. Sorry about that. Yeah, thanks. So this is just really a matrix product state. We've seen a number of times, including in yesterday's talk. And this n, so these are n by n matrices. Since I'm working U and gauge theory, and so this is just a matrix trace over n by n matrices. And so if I want to compute one-point functions of operators, really I need to take these traces that I have here and just substitute all the classical values. And a convenient way to do this is just by taking an overlap between this boundary state, which includes all this information, with these beta eigenstates, so these solutions, these eigenvectors of my dilatation operator.
Sorry, why do you call it a boundary state?
Yes. So the word boundary state is really just a name. You can think of it maybe it's better to think of it as an initial state. It's really like an initial condition that you have, but then you can essentially rotate it, and it looks a bit like a boundary.
Maybe it's like the Shibashi or Cardi condition.
I mean, this is just a spin chain, right? It's just a quantum mechanical system. It's not a CFD.
How do you know that this describes your defect?
How do I know that this describes me?
What is it?
Because I've introduced this omega here. That depends on the defect that I've introduced. Right? So depending on the defect, this omega will take different forms.
Sorry, there are something like this from the first principle, like they start with the correlator and the insert defect operator, and then large n expansion, then this comes down to 9, so they're not interbinary.
I mean, really, all I'm doing is I'm really doing something very stupid, right? I'm just taking all the operators. I'm just taking an operator of this type, right? But I want this operator to be an eigenstate of my dilatation operator. So I need to include permutations of these, right? And then I want to take this whole thing, which includes all these funny permutations, and insert the classical vebs, like the vebs of the operators that I have that describe my defect. It's just a combinatorics problem, and it's just a bit tedious, and this is a neat way of doing it. That's all I'm saying. Okay. And now I can do this for any defect I like. And generically, I'll get at a complete mess. So I'll get something that depends in a very complicated way on these U's, and it will be not universal. However, if these integrable charges, or let's say all the odd integrable charges, annihilate this boundary state, in which case we say that the defect is integrable, or the boundary state is integrable. Then we can actually find closed form factorized expressions, or these overlaps, that hold for any length and any number of excitations that you have. This is kind of where integrability comes in.
The expression for the higher charges in terms of the roots.
Sorry, I didn't understand the question.
Is there an explicit formula that gives you the higher charges in terms of the solutions of the...
The higher charges do not depend on the beta roots.
Yeah.
No, I can construct them out of the Hamiltonian.
But on each state, which is classified by the beta roots, it should take some value, which depends on the roots.
So the charges are really just, I take my Hamiltonian and I take commutators of each two-side state.
Yes.
And then so that's how I construct the third charge. Then to go higher, I essentially need to look at something called the boost operator, which again contains these elements of my lower charges, and you can just recursively construct all these charges.
But then you should be able to diagonalize all of them simultaneously, right? Because they all commute.
Yes.
So this beta root state, they don't do that?
No, not necessarily, right? I mean, they're just eigenstates of the Hamiltonian. That's all I care about at this point. Okay. What was I going to say? Good. So the point is that, if B is integrable in this sense, then you can really write down an infinite number of one-point functions for an infinite number of operators. I mean, okay, in this case, this is really just tree-level one-point functions, but in some cases you can actually go beyond tree-level and use symmetries to find one-point functions to all orders and perturbation theories in the 't Hooft coupling with just tree-level stuff as input. So it's actually very useful. So let me just mention very briefly what these boundary states could look like.
Sorry.
So, yeah.
Can I ask you about this boundary state?
Yep.
This thermodynamical limit.
Yeah.
Is this boundary state normalizable?
I'd expect the answer to be no, but I'm not entirely sure.
For finite n is normalizable?
Sorry, finite n or finite L, the length of the
L.
L. Yeah, true. Yeah. I mean, everything is finite. Okay.
So the thing that we don't know is how to take the thermodynamical limit, or?
I think it is understood. Actually, a lot of the... I think it is understood. I just don't know so much about it. One thing I can say is that when people find all loop expressions, really what they mean is precisely the thermodynamic limit. They call them asymptotic one-point functions in this case, because you really need the operators to be very large, so you can ignore effects of wrapping around the spin chain. So you can have excitations that self-interact and feel the finite size of the spin chain. And those are non-perturbative effects in the 't Hooft coupling. And to suppress these, you need to take the size of the spin chain to be very large. I'm assuming is precisely the thermodynamic limit is effect. So yes. Good. And so let me just very briefly sketch what these one-point functions look like. So they were first discussed in the D3, D5 system, which is some kind of interface CFT. They take the form that should be somewhat reminiscent, right? They involve some SU2 representation matrices. So they were first written down just at tree level. People found new results. And then by degli, Christiansen and Zarembo, and then they were generalized to an all loop expression by Gombar and Beinuk just 5 years ago, I think. So that's one set of boundary states that you could look at. You could also look boundary states for a Tuft line. This is a Tuft line. The field looks something like this. This is just a constant vector in R-symmetry space, and then B is a diagonal matrix. So again, should look somewhat reminiscent. So the question that we wanted to ask was, what sits here in this column of this table? And in the last maybe 20 minutes or so, I want to maybe try to convince you that these operators that I introduced at the very beginning, these surface operators, which I argued were essentially the simplest, or analogs of the very simplest possible thing that you could write down in gauge theory, that they could sit in here. Cool. So now I can finally show you some results. So one-point functions for surface defects. For precisely, so we'll start. Since we have two kinds of versions of these, let's start with these guys here and see what happens. So it turns out that the SU2 sector is kind of boring, so I will not say much about it. I will say some words about the SO6 sector. And so what you find there is that you can write down a boundary state, just very explicit. Just so you see what this looks like, and then I'll be less explicit later on. Right, so I sum over all the betas and gammas that I have that enter the definition of my surface operator. And I can construct the state, and you can check that this state is annihilated by the first odd charge, and actually all the other odd charges. So it's integrable. And so to find overlaps, I need to compute the one-point function. To find one-point functions, I need to compute the overlap between this boundary state and the eigenstate of this beta eigenstate. And so the way this works for the SO6 plane chain, it's analogous to the SU2 case that I discussed. It's just a little bit more complicated. You have three types of roots. So three types of beta roots, each corresponding to a node of your SO6 Dinkin diagram. So you really have three roots here. And then the result is, will be somewhat schematic. There's something that depends on beta and gamma squared. And then times some times some perhaps a bit scary looking expression, but it's actually really simple once I tell you what these functions are. So these Q functions, they're really just functions of the beta roots of a given type that I have, and they're just given by products. Over all the roots, just shifted by some number x, which is either 0 or 2. And these g plus minus, they're essentially just logarithmic derivatives of the beta equations. Orally. So this is what I mean by yes, sorry. This is what I mean by factorized form, right? So for any solution to the beta ansatz equations, any length u, any distribution of these u's, I can write down this equation that depends universally on these functions. So really this expression captures one-point functions of an infinite family of operators.
That's just leading order in Utoph coupling.
At leading order in the Utoph coupling.
Where is lambda here? Lambda's
Uh,
not there.
Lambda is really enters in the anomalous dimensions of your operator.
So it's not here at leading order.
It's not here at leading order.
Andy asked about boundaries, so this is codimension 2 now?
Codimension 2, that's right.
Should I really think about it as a boundary? Is it more just like a background state or something?
I don't like the word boundary state, but this is the terminology that people use. It's probably better to think of it as an initial state on your spin chain.
Yeah, I think, yeah, if I rotate this way, then boundary is here, and then it must be integral boundary where factorization is preserved by the boundary. That's what
Exactly. But in the way that I've presented it, it's really just some state on your spin chain that encodes the information of the boundary. Oh, sorry, it encodes the information of the defect.
Closed spin chain still, right?
It's a closed spin chain, that's right.
So it has no boundary.
It has no boundary. That's why I prefer to think of it as an initial state.
And your spacetime is 4-dimensional.
My spacetime is 4-dimensional.
And your defects are 2-dimensional.
Exactly.
So what's the boundary?
It's, as I said, it's really just the initial state on the chain. Right.
This is really like for any just classical configuration of the scalars.
Yes. Any classical configuration, any codimension, you can do this.
So it works for all three of those cases.
It's exactly the same. The only thing that changes is this omega. Right? So where I have to use different expressions for this omega, depending on the physical defect that I'm considering.
Nothing's changing at time t equals 0. And I've had this defect there for all time. And I'm asking what the expectation value is of this closed spin chain operator. We'll see why that's a boundary.
That's why I don't like the name.
The spin chain, the time evolution is like, your Hamiltonian is like the dilatation.
Yep.
So the quote-unquote time evolution is like dilatation.
In space-time, on the spin chain, I'm not sure it really makes so much sense to talk about time evolution because it's really just you just care about eigenstates, right? You just want states that are stationary.
You want to treat this as an initial state.
yeah, since it's stationary, you can think of it as a time evolution sitting there, but it's just trivial. That's what you say.
Yeah.
But the B is not an eigenstate.
B is not an eigenstate.
So there is no time evolution in this. So it's, I think it's better to think of it as a background or some fixed state that you use to start this process.
Fixed state, maybe not initial state.
Background state.
Sorry?
Background state. You should still use B.
Yes.
This is for like scale invariant or conformal classical configurations.
Correct. Good.
Is it the most general? It's this matrix product state. Couldn't you have more general? More general than a matrix product state?
Yes, you So here I just wrote down a single site state. I think you can have more general states where you have what's called two-site states that repeat, where basically a bunch of two sites next to each other. It's still something like a matrix product state. Matrix product states, I think, in general are close to the most general things that you can write down in integrable these integrable systems. Or most general in the sense, most general useful states that you can write down. There are more specific states that you can write down, things like valence bond states, or like this state, which really is just fully diagonal. Right? This matrix is really, the trace just becomes a sum over all the diagonal elements. So there's nothing really, it's not really a trace anymore. You can treat each of these separately, each of the summits.
So any integral boundary conditions, can they be interpreted as some classical background? Or?
So if I can interpret my defect as a classical background, then I can construct a boundary state, background state on my spin chain.
How about the other way around? Can you start from the background state and then find out corresponding solutions?
It's a good question. I don't really know the answer. I know of examples where there are background states that have certain symmetries, where you can write down a boundary state and it's integrable and everything, but it's unclear what what defect that corresponds to physically. I don't know of a concrete recipe to really. So I mean. Yeah, so of course you can, if I give you a boundary state, you can reconstruct what kinds of data that you have, but it's unclear how the system is really realized in the quantum theory. I don't know if this answers your question. Okay.
Just struggling with it. So you're using these beta ansatz beta ansatz for the spin chain in this background. Is it obvious that you should still use beta ansatz now that you have this?
So the beta ansatz doesn't care about the background at all. It's just a property of the bulk. It's just a property of the bulk, right? It's really just a statement about the spectrum of n equals 4 superheterosis theory. And it's just convenient for us to use that to compute one-point functions of eigenstates of the dilatation operator, of sort of operators that have well-defined scaling dimensions, at least to the order and perturbation theory that we're working on.
Don't you need that the state is integrable?
In principle, no. It's just, you can do this for any background that you like, but you get a mess generically. And these factorized expressions, you only get when your state is integrable. Okay. So, yes. So we studied the SO6 sector, we were very happy. And I think I gave a talk at ENS last year where it's about something else, but then I hinted about some integrability for these surface defects. But then we went on to study the SL2 sector, which I said was closed beyond one loop. And what we found was that already the first odd charge does not annihilate the boundary state. And we were sad. So we can only find closed form factorized expressions in a very special case where I think I erased it. Where I just have two derivatives, but that's kind of trivial. You can always do that for these kind of systems. So more generally, it really becomes a complete mess. We were not able to find a closed form expression. And so But not all hope is lost, because there still is this other system, which are these rigid surface defects, and you can play the same game. Right? So rigid. You can play the same game, and you construct a boundary state. So you start in the SU2 sector. Already the SU2 sector, you can construct a boundary state that is integrable. And so if you remember here, in my rigid setup, I had this extra parameter k, which corresponded to the dimension of my SU2 representation. And so this boundary state is actually integrable for all k. Integer, all the integer, positive integer k. What else do I want to say? Yeah, maybe I'll. Yes?
I'm lost. If there's no such defect, I believe we can still construct some kind of state like V.
If there is no such defect.
Right, so you turn off this background field. Or
I mean, the background field, it enters through here, right? So if I turn off the background field, my boundary state goes to 0.
Needs the background to have a non-zero one-point function? Is that the question?
Yeah. I see.
Yeah, that's right. At least in this order, right? I mean, I want to have a non-zero one-point function already at tree level. Okay. To say. So the SU2 sector turns out to be integral for all. And if I look at operators of the type I just erased, so just built out of scalar operators, we find that we can still construct boundary states. Well, these are only 0 provided that k is equal to 2. So only when my SU2 representation matrices are Pauli matrices. And then we're again able to write down, some simple-looking boundary state that depends on a bunch of Q functions. Just to give you an idea what these things look like. It's even simpler than the one that we had up here. And so, as before, the real test was the SO2 sector. And there it's a bit more subtle, because if you remember these field configurations, they have logarithms. So if you, in the SO2 sector, we're instructed to look at operators that look like this, where I'm taking derivatives of some classical field configuration. And that's generically going to create a whole mess because of these logarithms in the denominator. But as I argued earlier, one should really be agnostic to everything that comes in at subleading order as we approach the singularity. So if I throw all of these away, so really I'll have something that goes like classical will look like something in log r 1 plus order 1 over log r. This thing is very simple, and then I can construct a boundary state in terms of these guys that actually is integrable. Again, it's 0 only if k is equal to 2. Sorry?
It's enough to check only Q3.
Generically you have to check all the higher charges. I don't know of a single example where just checking Q3 doesn't work. We also checked all the other ones. But Q3 is the easiest one that you can do. You can just put it on a computer and it works it out for sufficiently small spin checks in like seconds or minutes. Okay, and we again find overlaps that look very similar to the things that I just wrote down for the SO6 sector, also in the SO2 sector, and the SU2 sector, which I didn't have time to discuss. And so, really the point I wanted to make in this talk is that it looks like what sits here in this table is this rigid Google-Witten defect, k is equal to 2. I put a question mark in here because I've only shown this at tree level. But we've checked a bunch of sectors. It works in all those sectors, including one that is closed beyond the one loop level. So this is really what I'd like you to take away from this talk. And so this is really the punchline. So it looks like, so we have good indication that if you start off with this defect and you take this limit where you send alpha, beta, and gamma to 0, such that the subleading singularity takes over, you get this kind of system. In this particular corner of this defect parameter space, it seems that we have an integrable defect. Okay. So everything I've said, of course, is only true at tree level. So the obvious question is, okay, what can we say about about loop corrections? That's where things get, this is the obvious thing to check. But things get a bit tricky because of these logarithms that you have in there. And so usually what you would do is you would take a field configuration. So you can do this, for example, this paper here, with this defect here. And so you plug this into your action and look at fluctuations around this background, and you treat all the interactions perturbatively. And you find a propagator that is actually very simple. It's just relatively simple. It's just a hypergeometric function. However, if you try to do the same thing with these logarithms, it's a complete mess. The differential equation that you need to solve includes logarithms of all kinds of powers, and we haven't been able to solve it. And probably, it seems to us that this is probably not the right way to quantize the system. What else did I want to say? Yeah. However, I do think that we have also indications from string theory and ADS-CFT that this thing is integrable. So, for example, this defect you can think of as a D3 probrane on ADS3 times S1. So D3 on ADS3 times S1. Where this probrane is embedded in a kind of funny way, right? In a way that mixes the radial direction around the defect in the boundary of ADS with the equator on the S5. But if you turn off all these parameters, the defect just traps ADS3 times S1 in the obvious way. So the ADS3 part is just in the ADS, and the S1 just traps the equator on the S5. And you can look into there's this paper by Decker and Oz where they classify all the integrable boundary conditions of the string worksheet. And you can look in that paper and you see precisely this configuration appears in this limit. We've taken all the parameters to 0. So this is hopefully where we're going. I should also say that a lot of the hard work has already been done for us in going from tree level to all loop asymptotic formula. There was a paper by Yingfeng Zhang, Eduardo Vescovi, and Shota Komatsu from I think 2019, where they look at n equals 4 without defect, and they look at the 3-point function of 2 determinant operators and a single trace operator that's not protected. And they're actually able to map this. They map this 3-point function onto precisely the kind of problem that we've been working with here. So it's again an overlap between a boundary state, where the boundary state encodes the data of this guy here, and some beta eigenstates.
So what is this D operator? You said
It's a determinant operator, so it's yeah, so it's a determinant of basically all the scalar fields. And so instead of taking the trace, you take a determinant of the matrix structure. And so yeah, so not only were they able to find tree-level expressions for these 3-point functions, they're also able to find an asymptotic all-loop formula, which they were able to bootstrap using using symmetry techniques, and then using a weak coupling analysis to fix some function that is left unfixed by the symmetries. And it turns out that the symmetries that appear in this 3-point function are precisely the same that appear for the rigid co-covariant defect. So all the hard work of incorporating symmetries has already been done. The only thing that we really need to do is to fix this overall function, which hopefully we should be able to do using a weak coupling computation. Yeah, I think maybe let me just say that as I think as I've said earlier, there are still many basic questions that are to be understood about this defect. Questions about how to quantize around this, but then also second order questions about how does this system really appear in holography? Are there any backreactor geometries? Since the system is supersymmetric, it could ask can I do localization around this? And I should also the last thing I'll say is that in this talk I've only considered defects that preserve 2D n equals 4,4 supersymmetry. There are also defects that are chiral, so 8,0. You could ask, are there any integrable ones among these? And I think I'll stop here. Thank you. Sorry for going on.
I'm a bit confused about how the D3 on ADS3 process realizes this defect. Because if you want it to like the embedding to be realized as SU2 matrices, I'd expect it to be wrapped on like a 2-spin.
It's so usually that's kind of that's what happens for the D3 D5 system, where you essentially have D5 brains wrapping a 2-sphere, and then you have to turn on some volume flux to make it non-commutative. Here it's a bit less clear what's going on. I agree.
But can you find solutions that solve Pound's equations and that are SU2 matrices? The probe D3.
I'm not sure I'm following.
So is the D3 like a fuzzy D3?
So I don't think it's really understood. In the case of the ordinary defect with the continuous parameters, there is nothing fuzzy about it. All I'm saying is that in this limit, the embedding of the D3 brain becomes one that suggests, one that corresponds to an integrable boundary condition of the string. Then there is still a step that, I guess several steps that you need to make in relating this configuration precisely to this rigid defect. It's just at the level of an indication at this point. But as I said, there are many questions about these rigid defects that remain to be understood, and this is one of them. Yeah.
Just what you said is about n equal 4, right?
Yeah.
Is something known for n equal 1?
N equals 1.
Yeah, you know, this everything the whole integrability business is tied to n equal 4,
yeah.
No? So
yes.
If you go, but yes, if you can use the conifold, change S5 and change this Sasaki-Einstein thing, and you go to n equal 1.
So I don't think that you would still preserve integrability. People have tried to go to n equals 2 by taking orbifolds of n equals 4. So
n equal 1 break integrability completely. I'm asking.
Sorry, you want
So
to...
you think that n equal 1
I think
cannot
n equals...
construct any spin chain.
To my knowledge, yeah. I think it's only very special special things that you can do to n equals 4 that preserve integrability. And I mean, also you'd have, if you wanted to also study this particular defect, the more supersymmetry you break. So if you break down already to n equals 2, then this thing has to be 0. So you only have the gauge field itself. It just becomes an analog of Maxwell, or the surface defects that you have in Maxwell theory. And then this whole techniques you can't really apply, because the field strength itself is just delta function localized on the defect.
There's the statement, I forget who made it. It's this deep statement that vacua of 4-dimensional n equals 2 theories are in 1-to-1 correspondence with integrable.
There is this whole industry of relating
Like,
2D n equals 2 gauge theories to the models. These are
AGT,
as much about it. But there are analogs of these. So I think those are really. This isn't quite the same type of integrability that we're discussing here. I don't think there's a spin chain that would be as.
okay, that might maybe.
I'm not an expert. I don't really.
I had a more general question though. Using integrability, can you compute anything besides scalar one-point functions?
So in these systems, you pretty much can. You can compute all one-point functions of. You can compute one-point functions of operators built out of an arbitrary set of fields.
Not just scalar.
Not just scalars. Because you have expressions for one-point functions in the full PSU2,2/4.
For codimensional and defects, aren't scalars the only ones that get one-point functions?
Right, but you can still have scalars that have scalar operators that are built out of say 2 functions.
Oh, okay.
So that's the kind of stuff that you can compute in the DCFT context. In ordinary gauge theories without defects, people compute things like 3-point functions. There are these kinds of methods that involve hexagon form factors, where you can basically take, so like single trace operators, you basically take them as the endpoints of like a pair of paths, cut them open into hexagons, and then there's all kinds of gluing techniques that you can use to get the 3-point functions out of them.
So maybe someday people will compute 3-point functions with defects.
Maybe. I don't think anyone has really tried. I think that would be very interesting. Yes.
I mean, I didn't fully understand, but somehow you were talking about taking a limit where alpha, beta, gamma go to 0 and going from one surface operator to the other.
Yes.
So is there some picture or just some cartoon even in the DCFT corresponding to the alpha, beta, gamma non-zero case? What that means? Like, would this be some perturbation by some, I don't know, relevant operator in the defect CFT? Or?
I don't have a good answer. I mean, the way that Guker and Witten argue it, it's quite abstract, and they just say some words that I don't fully understand. I don't have a concrete way of getting this.
Because I think like some log type behavior also occurs in line in certain cases where you have lines and deformations and some RG flows that sort of don't end. I wonder if there's some similar story.
Yeah, I don't really know. It's unclear what the scale that accompanies the logarithm really is. I don't know if it's dynamically generated or if it's something that you have to put in by hand. But yeah, that's kind of what I first thought as well. So maybe they just correspond to some defect RG flow that keeps
Maybe some scale without conformal invariance or something.
Yeah.
It's not normal.
should stop there. So let's thank Adam again.